Hello there. I've done a number of videos on monitoring ThingWorx and ThingWorx solutions using various performance metrics approaches, as well as building and maintaining a number of dashboards that are used for such. One of the things that I'm aware of when I speak to people about this topic is we're not monitoring for the sake of monitoring. We're monitoring really for understanding things like health, availability, responsiveness of services that are provided by the applications that are running in ThingWorx. And this is a very complex topic because we really have many different layers that are in between the infrastructure as well all the way up to the running application within ThingWorx. There's the database, there's the OS level, there's network aspects, there's disk persistence. So it really depends on what's happening on the environment as far as how the overall application is going to be behaving and responding. This could be as simple as like a web server serving out some resources from Tomcat, or it could be a lot more complex, like reading files, regenerating new ones, serving dynamic data from ThingWorx out to a user. But one thing is clear is that this is underpinned by the database. ThingWorx platform is a database application that relies heavily on that database application for its overall operations, things like storing something in the model. These things all go back to the database, and there's a number of functions and operations that are included in the platform and that you're likely going to build into your applications built on ThingWorx that also require that database layer. Data tables, value streams, and streams. There's also possibility of using auditing mechanisms. So whatever this all looks like, the question is then what parts of this infrastructure is going to be shared. Maybe you have multiple databases, maybe it's a shared database, maybe you're doing different things in high volumes. It really depends on what the overall system design looks like. But as we're learning about these things and as we're talking about these things, we typically don't have concrete cases that we can explore. What does work well is a little bit boring to look at because the lines typically look flat and uninteresting. And so today what we're going to have a look at is the opposite of when things go badly. And we're going to use this as an opportunity just to show you kind of some of the things that essentially knock the dominoes over or make the house of cards fall over when you have multiple things that cause cascading effects onto other systems. So let's get into it. We're going to start with looking at some metrics in Grafana, and then I'm going to go to the whiteboard and we'll discuss about some of these things and how they impact one another. Okay, so first a little bit of context about what we're looking at here. This is a ThingWorx Foundation dashboard that I've been maintaining over the past couple of years and will continue to. This is a ThingWorx high availability cluster with 3 nodes of ThingWorx and doing mostly file transfers. There's some logged properties that are coming in, so data item updates, logged properties. And there's some stream entries that are happening based on some events. But in general terms, it's doing audit events, it's doing file uploads, and it's doing log properties. So we'll kind of keep it simple. This is about a 2-day period in a load testing environment where we're essentially looking to prepare and ensure that an application is ready to go into production and understanding the limits of the system. And we can see here kind of for the first day, this is beautiful, right? This is memory use in the top. This is coming from the ThingWorx metrics. Most of these come from the ThingWorx metrics endpoint. And nice and low and pretty solid across all of the nodes. And you can see this for this particular period here. Progressively over time, memory use increases, and to the point where the second day you can see it's really quite high. I'm not saying that this is abnormal for what for this particular application, but certainly we do see increase in memory over time to a very high level, whereas for the first day it was running quite smoothly. something we need to keep in mind. We will have a look at the singleton up here. Singleton, this is indicating who's the leader of the cluster. And normally this shouldn't change. But if I put my mouse over in Grafana, I can open it up and we get the little kind of some visuals that show up here. And we can see that the singleton has been changing over this almost 2-day period. I don't know what size those are. Maybe they're 8 hours. But in any case, it runs for 8 hours and something is causing it to change. Election being forced like this means it's either gone or it really can't respond. So Zookeeper is going to initiate the election for it. In this case, I believe what's happened is the liveness probe fails after a number of times in Kubernetes, and Kubernetes is just going to kill it. And so leader goes away, we re-elect a new one, we move on. That new one becomes a leader until the problem essentially continues. 8 hours later, the same thing happens. So if we just kind of look at the WebSocket execution tasks that are being submitted here, you can see they're quite flat, quite stable across the 3 nodes, giving us a good understanding that whatever work is coming into ThingWorx, there is no user load here. This is all device load. It's quite stable. We see some kind of hiccups as we're getting started here, but otherwise it's quite flat. It is a little bit strange down here when we look at the event processor that the event processor shape and rates are not, so they do not track what's coming in. That's something that we should and will keep in mind because while we've been running tests, normally those two have tracked quite closely together, other than if something else is going on. And this something else that's going on is what we're going to talk about. Event tasks can come from many different places, right? They can come from elsewhere on the system. They can come from the WebSocket execution subsystem. They can come from REST API calls. They can come from timers that are triggering things, services, subscriptions. Subscriptions are big ones. Subscriptions live within the event processor. So if we subscribe to something somewhere and then run any code from it, this is where it lives. Oh man, I'm giving away the secrets too early. Let's look at the event queue and the thread status one here. This is kind of a weird graph. I tried to pack a lot into this single dashboard, but what we're looking at right here is actually hiding something. I'm going to hit V and we'll look at it a little bit closer. But the first thing that we notice is the colors and these spikes, right? So this is event queue. You can see queue size P0, P1, P2. And I've just added to the legend here, the last, the min, and the max. So you can see that they're pretty much all getting up to 200,000. And 200,000 is the default configured limit for the event processor that we can work up to that, and eventually it's going to spawn more threads in order to try and get the work completed that has been queued. And it will spawn a X number of threads, which is potentially relative to what's going on. But in this case, it takes some time. How long is this time? 22, call it a couple of hours in order for the thing to get all the way up to the top. Here it's okay, right? Here this is fine. This is what we would expect. The blue one here, it's getting started. So while it's loading, while it's essentially initializing, we have a period of queuing on the blue node, the 2 here, P2. And then it does the job, does the work, finishes, gets down. We have these periods where it comes up to 20K for a little while, a couple minutes, work gets finished, and it goes back down. This is all good. This is not. The part that's hidden in this thing, you kind of have to use the legend in order to make this shine through, or you can actually edit it and then just hide the queue size. Why don't we try that? E for edit, and let's just hide the queue size here with the little eyeball there, and apply. And now, so you see that it's a different legend. That's why we didn't see anything really previously, because it's a very different scale when we look at the active threads. 6 or 12 or 50, it's not going to show up when we see the 200,000. So here we see essentially the other side to the event queue is the active threads in the event processor. And here you can see during that period in the middle when we had some things coming up and then going away, we actually bumped it up to 64. So normally this is quite low. The default pool size is 16, the core pool size. And I don't have the core pool size on here. There's only so much that I wanted to put on this graph. But it's important to note think about the maxes. I might have raised the core pool size on the kind of previous page there, but think about the maxes and the active. Right here, we clearly know that we've got a max that's the core pool size is 16, and if we look in this period, you got one or two threads that are active across the different nodes. There's not really a whole lot going on. When we get to those kind of spikes in the middle where we saw 20,000 events coming into the event processor, it goes up to 64. So it is pushing that number of active threads up. I say the default. I've probably put this to 64, otherwise it wouldn't have gone up to 64 so quickly, because of the fact that there wasn't that many events in the queue. So it's possible I have made some changes on this system. But in any case, we get to this period where we saw the queuing starting just to go up and up and up. What we see is our actives that were just every once in a while busy for a moment become stable, right? So here we have 64 that are active all the time. And this is what, over 1 hour? So this is 1 hour. We have 64 threads that are constantly busy. This is not a good sign. This is indicative of the fact that event processor has work that it's doing. It's not available to take anything new. Queuing is either happening or it will be momentarily. In any case, the event processor is quite busy. And although that is normal and expected and by design, this is an indicator that we need to think about. Is this healthy? Is my application responding? Does this mean that HTTP requests, REST API calls, user interaction is going to remain fluid at this point? Because these are what are responding to those users. Gets to a point we hit the 200K. That's probably about here. We hit the 200K. And the platform responds by saying, we're not getting it done. We need more help. We throw more threads at it. And here you can see it runs for some time. I don't know if that's 30 minutes or so, but it runs for 30 minutes or so with 500 threads that are active. In a lot of cases, this would do the job. This would, and we saw in this load testing actually, that it really brought down the queue and it got the work finished, did more file transfers. It got caught up in a couple of hours. So it's really the behavior that we would expect of and how the event processor is designed. Problem is, as I mentioned, not responding to users. This means also not responding to that liveness probe. Kubernetes kills it. And all of a sudden, this busy environment goes back down to 0. And we cycled through the 3 of them. One thing that's a little bit different about this graph here, if we maybe reactivate, I can just discard this perhaps. Discard, no, I can't, I already applied it. So we'll put the queue back on there and apply, and let's come back out to here. Can't remember what I was going to say. The queues, active, busy. Doesn't matter. Oh, right. Yeah, I know what I was going to say. Let's look at this one. We're going to compare this one to this one. Okay, oh, it doesn't matter. This one to this one. Execution task submit rate. Here, this graph looks quite different, right? We know the same thing happened on the platform, but here you can see that these are stacked, and we've got one on top. So this is a cumulative graph of submitted tasks per second. So here we got a total of about 400 tasks submitted per second. And they're quite balanced across the 3 of them, right? So this is normal. This is how the load balancing is built between the connection servers and the platform. We're going to have this work distributed across the different nodes. Okay, so this is good. This is balanced. Considering that the traffic that is going to be coming into the nodes is likely somewhere along the line is going to create events. Those events might be subscribed to in order to do something, like to log them, for example. The fact that we see something like this here tells us something. It tells us that this is related to the singleton, because this is only happening on one of these nodes at a time. And we can validate this, right? P1, we can look at this. P1 was the start. And if we come back to the singleton up here, we can see that P1 was the singleton for this period. Then we went to P2, then we went to P0. Is that what we see here? Blue 1, P2, right? P0. So this gives us a really good indication of what's going on here, where this source is coming from, because singleton handles timers and schedules. We don't want those timer and scheduler kicked off work to be executed across multiple nodes, just so that we can maintain control over that execution. Presently, that execution is done from the singleton. So what we know by this is that this is singleton generated, right? So we need to be thinking about our timers and our schedulers that are kicking this work off. And I would bet, I haven't done it, but I would bet if we looked at these, we would be able to find a match. It's about 10 minutes between these spikes, okay? 10 minutes between these spikes. The reason they're so perfect is because they're tied to timers. Amazing. So what next? This is where we start to get interesting. So this is database connections. These two graphs are leveraging an API call that's relatively new in the platform. This is kind of some magic that you might have seen in previous videos that we really had to get into JMX attributes to get access to, but there's been a resource that's been added to get access to database persistence metrics, and this is the result of that. That gives us some metrics to know how many busy connections and how many active connections we have for the persistence provider. So this is the ThingWorx persistence provider. This particular project only has one persistence provider. But we could imagine having different ones. If we had multiple persistence providers, we'd see them all in this list. And it looks like, yeah, there we go, that's better. I had only selected one. So you can see that this graph has busy and active. We're going to do what we did on the other one as well. Let's just come in here and we're going to busy. Yeah, so unfortunately this new API that I just mentioned doesn't bring out max pool size like I've done in the past, shown in the past. So we don't have max pool size. You're going to have to go into the platform to look at that, but that's obviously fixed. So you should know what that is. We know the default is 100, and we're at that 100 limit. And busy connection. So what did I just hide? Busy and active. Okay. So active. Yeah. So here's the active connections that we have established, right? These are one thing that's a little bit strange about looking at metrics like this is think about a lot of the database activities and transactions that happen. They're very fast, right? So we're not going to capture everything that's going on. It doesn't mean that X doesn't mean that 14 were active within this time slice. It means that the moment that we took a time slice, we called this API to get these metrics, it means that there was 14. So this gives us a trend, it gives us an idea, but it doesn't tell us that the max in this range, right? But we clearly see that we do have some periods where we're getting pretty high, right? This is up at 100. And if we look at the other one, here we can see that active connections, so active connections, they're going to have a longer life. The busy connections, it's very fast, right? The active ones, we're going to make some connections in the DB connection pool to the database. Default setting is to hold on to those for 5 minutes before we do an idle check to see which ones we're going to just disconnect and let go of. We want to maintain those connections if they're going to be reused. So this means that, you know, this blue line here, P2, This is stable at 100 for quite some time, meaning that there's enough transactions that are using those connections. But in any case, if we just look across the board, pretty much the 3 nodes are at their max. It says last. I could probably add some. Let's put average in here. Mean, max. All right. So on average for this period, about 75, 80 connections, meaning we're really at the high end of the limit, right? So database connections are not fully saturated. And I guess that's where we come to the neighbor on here. This cool little percentage that you can use in your applications is same sort of deal, but it's just represented in a percentage. So it doesn't show us what the max is, but it is going to show us how many, it's called connection pool saturation, how many of the connections are in use at a particular time. And you can see as we kind of go through some of these phases, a lot of them are maxed out. This one's at 100% at this particular time. This you can use in your application and in your monitoring setups. Definitely recommend that you use this connection pool saturation, and this is kind of what we're talking about here. So if we say, wow, okay, this is busy, right? This isn't great. This isn't great. What else? What if we look at some other things? I prepared some other dashboards. This one is the application gateway. Just because I had some kind of metrics and I wanted to have a look at what else was going on at the particular time. I mentioned that this is WebSocket device traffic, and just so happens that all the devices are coming here through the application gateway. And so this kind of gives us some ideas. Do we see some patterns in the I don't know what to call this, during the load periods across the previous one over here, right? Here, here, and here, and here, 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 and here. Yeah, we definitely do. Looks pretty good. We do see these failed requests in the middle, which means that after the singleton is restarting, there's some errors that are going back, and this is likely due to the fact that the message connector is probably not responding favorably to those devices while that the cluster gets restabilized. And right, other than that, nothing really great. Everything looks pretty much okay other than during these outages. So this didn't really tell us a whole lot. We could check things like, this is what I was looking at, a server backend. Do we see different errors on the server backend? We do see that we're getting some 400 errors, not a whole lot. What about 500 errors? Yeah, so there's a couple of 500 errors, and they are coming up as well during those outages. Okay, so moving on. Obviously, under a lot of pressure, we're seeing this not able to keep up appropriately. We want to look at CPU resource utilization, right? CPU and memory. So here we are in looking at the Kubernetes compute for the namespace. So this particular graph is a little bit hard to kind of dig into because of the fact there's a lot of different applications that are running in the cluster. And this is really, this was the first chunk that we saw that was things were running pretty good. And, you get the purple one here, ThingWorx, and I was going to say, and Ignite is the other one, right? This is normal. It's a cluster. Ignite is the in-memory cache that's providing all these transactions back and forth. All these property updates that are coming in, as well as the file transfers, are leveraging and requiring the use of updating the cache. And hence, there's a lot of Ignite resource requirements, including CPU and memory. And same on ThingWorx. And if we look down here at the memory, similar picture. There's actually a lot more memory use here on Ignite than ThingWorx. So, we can see that it's actually the ThingWorx memory that's ramping up over time, and that's because we've configured those ThingWorx pods to start smaller and take memory as they need them, whereas Ignite is obviously taking a much bigger chunk at the start. Other than that, nothing really amazing in here. One of the things we do want to make sure, though, is that all these little components are running smoothly and safely. If they're unable to get memory, if they're unable to get CPU resources when they need, they will start to back other things up in the cluster, and that's what we're going to have a quick look at here. I wanted to just check for throttling. Throttling of the resources in Kubernetes is a big problem for things getting backed up. And really this is a question of resources being overcommitted or attempting to take resources that are shared between services, and Kubernetes either can't give it more resources, so it can't ramp it up to maybe closer to its limits, or maybe it's on a node that just doesn't have those resources available and it doesn't want to kill it and shift it over to another one. There's a lot of reasons for it, but in any case, it's going to slow stuff down. And if Ignite is slow, then that's a bad thing. Ignite is right in the middle of the application. It's providing the shared state for your stateful application. So let's start by looking at Ignite. And so this is on a per pod basis, right? So Ignite 0, you can see the limits up here, and everything is running smoothly, very much within the limits. Memory, same thing down here. Lot of room left there. Ignite 0, 1. We want to make sure that this is relatively balanced also across the cluster. And when we look at the 3 Ignite nodes, we do not see any throttling, and we see a good level of balance. E-message connector, let's have a look at this as well. That's interesting. You see the same shape in these, and this is because during the reboot, those errors that we saw, this is because we're not forwarding on to the platform. And hence there's this kind of silent period in there. E-message connector is holding back essentially. And ThingWorx, it's almost lower than Ignite. ThingWorx 0, ThingWorx 1, same, lower. And we can see that the memory pattern is matching what we saw on the ThingWorx dashboard, right? Just with the metrics from ThingWorx. So, they are very useful, just understanding the heap size and usage. And we can also see that they are kind of fitting with the profile that we saw across the cluster. Zookeeper, we want to make sure Zookeeper is running smoothly as well. It's doing a very important job in the cluster, a couple of them. Mostly service discovery. So for all those transactions that are going ThingWorx to Ignite, they're being essentially proxied by not proxied through, right, but directed from ThingWorx to Ignite. And you can see it's pretty busy here. Frankly, there's a lot of traffic going on when we're fully under load. And but in any case, all looks good. Nothing really worth observing there, but we didn't see any green. Normally here you can see this CPU throttling. This would be green. We'd have green bumps if we're getting into the throttling range. Any throttling isn't good. If we pass this red line, that's really not good. If it's just for a couple minutes, I mean, that's fine. But certainly if we stay in a throttling condition, then it means that the whole application is slowing down and is going to have difficulties keeping up. So let's look at network traffic as well. I really just wanted to have kind of a look at overview of the cluster performance and kind of some of the resources inside the cluster. And, we can see, nothing crazy. Progressively, it's getting larger. That kind of tracks a little bit what we're seeing with the memory usage increasing over time. And before, obviously, everything kind of crashes near the end there. What else? So storage. I mean, this is obviously underpinned by a shared storage. I mentioned there's a lot of files. There's obviously log files. And when we talk about constraints and bottlenecks, persistent storage disk I/O is a major, if not, the biggest kind of bottleneck that can present. So I just wanted to make sure here that, as far as the numbers of transactions, bandwidth, I/O, that we were okay on the shared storage, and everything looks quite reasonable. Moving along, So now we come over to the database. I mentioned this is Azure Postgres Flexible Server. And here we start to see some of these patterns, again, that we saw previously, right? We had, what, 3 chunks mainly? And we see these 3 chunks presenting themselves here, where we kind of start out around 18 or 20% CPU utilization. And the CPU goes up significantly to about 40. And this happens over and over. So I think now we're looking at those dependencies that the application has. I think we're onto something here. Let's just kind of have a look through here. So 40 isn't very high, obviously. So this kind of might jump out to some as saying, well, that's fine. I mean, I got a lot more CPU left in the box, and this is true. But CPU isn't really the problem here. What does this say over here? This here says 2,000 connections to the database. This says 3,000 connections to the database. If we think back to what we saw on the database connection pool saturation, that was maybe around 100%. The default is 100 connections, and so we have 3 nodes. That means that we should be hovering around 300. There's obviously some other applications, some other code that's going on here, things that are connected. But we should be under the 400 range, and here we're hitting peaks of 3,000. So that's a lot, and it's kind of like a telephone line. Just because the connection is established doesn't mean we're actually pushing work to the database. But this is a high likelihood that if those connections are open, that somebody's trying to get some transactions in there. And this is what is happening, right? So if we look at some of the other ones, not a whole lot of throughput. So this is like a tenth of kind of some of the major stress we put the database under, let's just say. So it's very, very low, and just totally fine. Same here. A couple hundred megabytes on read and write on network is fine. Storage, we got 512 gigabytes allocated, so storage is obviously increasing quite quickly because this is log properties going to a relational database. And IOPS, I mean, we have had spikes, IOPS to 2 and 3,000 IOPS. So I mean, this doesn't really kind of shock me, the level of IOPS here. What does shock me is the database disk queue depth. Here, normally this has been running at about, let's use this opportunity to zoom out here a little bit. So all of these time ranges have been pegged to the same time, so we're about to break the kind of pegging. But what happens if we zoom out a little bit? So this load testing has been running for quite some time, and you can see over here, if we zoom in a little bit, disk queue depth should be about 2, maybe 3, maybe 4. And this is really about us queuing up those tasks, those activities that have to go to the database pages, to go through them. And the more that we kind of pile these things on top of one another, the harder it's going to be for the database to get access to the disk and to make those transactions happen for us. And this spike to 30 isn't great, but not good at all, but it goes away, right? And you can see that we're getting these periodic spikes that are going quite high to 30, in which point the system is able to react. And you can see here we have the database connections at a relatively safe and stable range here, under 200. As I mentioned, we're not going to use those. So this is really perfect. This is what we've been seeing throughout the load testing. But these spikes coming up periodically gives us the indication that something else is going on in the database. And unfortunately, that something else turns into, I'm just zooming out so we can go back to the period that we were looking at right there. So we were going 10, 15, 30, and then all of a sudden over here, if we look at this pattern where the CPU goes up and up and up and up, up and up and up and up, up and up, is right in this area here. where we have the queue depth that is through the roof, over 30, even getting to 61. So this is an indication of a pileup, right, of disk heavy activities. Auto vacuums are in this. So, doing things like property updates, iStream, all these types of things have these automated maintenance tasks that are going to be running. But there's other things that we can do that can be very disk heavy. The point about this isn't what's going on here. It's really about thinking these types of things through. And we can see here clearly the database is not in a situation where it can respond in an effective manner. So if I did have service latency timing and I had done like a baseline, I'd be able to see that all of my services are taking longer. If there's a connection to the database, they would be 15, 30, 45 seconds because of the fact that everything has gotten queued up in the database and the database is unable to appropriately respond to requests. So coming back to the connections, if we come over to ThingWorx, database is super busy. What's going to happen is the transactions that are out to the database in the event process are going to take longer. As they take longer, they're going to build up. As they build up, they're going to use more more connections. As they use more connections, we're going to add additional concurrency on the database, worsening the problem. Right? So instead of giving the database some time to kind of finish what it's doing, we're just coming back and we're saying, this one task is taking too long. Why don't you do 2, 3, 4, 5 tasks? And this is what's happening, and this is why we see the active threads going up, eventually all to 500. As we go up to 500, if we were to match this and this together, we would see that at the 500, our database connections are going to be maxed out. And we're just putting additional pressure on the system. As the database is so maxed out, this is why these events are getting built up, because we can't get this work done because the database is taking so long to react. So we're putting this work in. We're saying I need to query this particular table. I need to make this particular change. Even things like persisted properties means we're going to have to wait on the database. We can't do the work. It's going to back up right here. It's kind of this is the big intersection. Everything is getting backed up, and it is essentially pushing back on the system to the point where the memory eventually goes through the roof, because this was another thing that this was a little bit unrelated, but it's one of these knock-on effects to it. Is the memory is going up because of the fact that they have timers and things like that are going normally to the database, does a query, looks at some data, and then it frees it. But when the database is super slow and can barely get anything finished, that query that should take 50 milliseconds now takes 20 seconds. And while we're 20 seconds, then we're going to have to hold on to that memory much longer. The system has so many more threads that are running. We've gone super parallel. We're going to have to do more garbage collection, so there's going to be more CPU used, and this just turns into us using more and more resources. So just wanted to kind of use this as an example. I don't think we're going to go to the whiteboard after all, but this is a situation where a database performance issue that we saw over here is causing backup in the database, which means that ThingWorx can't effectively do its job because it's got code that is essentially leveraging database functionalities that are not available. So this is maybe one of those where some of this is not so simple, but part of the reason I wanted to do this video is really just because of the fact that database connections, these types of things, is one of the biggest performance bottlenecks that we see coming up with ThingWorx. So you need to really be thinking about what are the persistence provider configurations? How am I leveraging the database? How is the database able to react and respond? For one, look at the max connections on the database. Depending on what database you have, you're going to have some max connections. You can't just have ThingWorx take as many connections as you want. Here, normally, we're supposed to be taking 300. You saw a moment ago that we're taking 3,000. So we have to make sure that the database doesn't start to refuse connections. We have to make sure that there's no deadlocks that are happening. But this is just one of those sort of reminders that despite the fact that ThingWorx makes a lot of things simple, we are still talking about complex applications that have complex infrastructure dependencies. And in order for us to ensure that they work well from the beginning and throughout their operation, we do have to get into some of these things and understand how they work. Okay, I hope you enjoyed this. This was maybe the first of what will be many more to come on the questions of what happens when things go wrong and understanding it. Have a great day.